Hello, my name is Brendan Thaler, and this is Physics 2212, Lab 4, Circuits Lab. So before I really get into it, I just want to do like a quick overview of what's going to happen. First, we're going to go over like the purpose of this experiment, the principles behind it. Then we're going to talk about the voltage and current in a series circuit. Then we're going to do some analysis with the parallel circuit. And then sort of the bulk of this experiment was with an RC circuit and RC calculations using a capacitor and calculating the RC value. And then we'll just have a couple reflection questions to end on. So the purpose of this experiment was to, first we wanted to evaluate the effective resistors in series and parallel, and then we wanted to measure the potential difference across different parts of the circuit, and then finally we wanted to calculate the RC values for a capacitor. So the first of the physics principles is the loop rule. This means that the potential difference across a loop is zero, and that's for any loop found within a circuit. So it doesn't just have to be like a series would have one loop, right? But like if you have multiples, like if you have like a parallel series, you can have multiple loops inside of it, and all of those have to be equal to zero. The node rule also means that the current going into a node is the same as the current going out. This is pretty intuitive until you get to parts where a wire may split, and the current may have to split going to different locations. And at that part, we will have to see, like based on the resistance, like what percent of the current goes where. Finally, Ohm's law, delta V equals IR, where I is the current and R is the resistance, calculated in ohms. And then the equation for capacitance, which is delta V equals Q over C, which is capacitance. Part 1 design, we predicted the current using Ohm's law, so we'd have 3 equals I times 147, which is the total resistance used in both of these resistors. And we got I to be equals to 0.0204 amperes. And then the actual current was that, obviously the sig figs took off the last two digits, but we can say that they're the same. And then when we turn the ampere upside down and had one port at the positive and negative than what it had before, we still had 0.02 amps. And then we took out the ampere and had an open circuit and did a voltmeter substitution. And so here we found that our delta V was 3 volts. And that's the positive voltage or potential difference on the right side coming out of the battery around those resistors, and then 0 on the left side because there's no current there. And we're assuming that this voltmeter has an infinite resistance so that there's no current going through it, so that the entire volt difference is found by that voltmeter, which we know is 3 volts because it's two 1.5 volt batteries. And so we actually calculated this at various points. And then, right after the batteries, so in between the first battery and the second battery, you're going to have a positive difference of 1.5. And then after the second battery, you're going to have that next 1.5, so it'll be up to 3. And it's going to stay like that until we get to between C and D, and that 47 ohm resistor is going to make the volt go down 0.959. And then it's going to be the same right there between D and E, and then after from D to F, it's going to go down another 2.041, and if you add those two up, you get 3 volts, which verifies the loop rule. In parallel, we had an amp meter set up before you get to the 100 ohm circuit. You can see that the current's the same. That's because since there's no resistance on like the path with the second amp meter, the current's going to go through there and basically skip over the ohm or the 100 ohm resistor. So the resistance goes 3 over 47, which is the voltage divided by that one resistor at the top right. So resistance calculations, we used R equals V divided by I. So we have, for those resistance calculations, we got something very close. The big difference probably just being from sig figs. And then because we had no change in volt from the wire and the amp meter, those are 0, because if you put the voltmeter in between those two, that's where it sort of plateaued. To make the RC circuit, first we just wanted to calculate times to charge and discharge different resistance bulbs. And there's my circuit that I did there. It's charging is when the battery's there, but then we connect the wire without the batteries. The capacitor will be discharging and the current will be going the other way. And then we took time and voltage calculations from a charged one. And so I just did times up to 20 seconds and then took those volt calculations and then did ln of v over v naught, where v naught equals 0.083, which I got from the simulation, and then wherever t is the time at which the charge is 1 over e of the original voltage, which would be 3.31 in our case. We got negative 1.66 for the slope, as you can see on the graph, and they make that equal to negative 1 over RC. So RC equals 6.002, which is comparable to the capacitance that we calculated. Just a quick reflection: if this were performed in a real experiment using a real ammeter, we would have different values because there's a lot of infinite and zero resistance assumptions surrounding like the wire, the voltmeter, the amp meter, like that there's no like the wires have no resistance, so there's like no drop of voltage across any of those paths. And so we're performed in a real experiment. We used a real battery and no resistor for the capacitance. We can estimate almost this like instantaneous charging time and like discharge time, or then like charging time, because of the small resistance of the battery and the wire, which is not necessarily zero, but close enough that we can say that it's going to be very fast. Thank you.